Well, I'm going to do some Sage math with some matrices just to kind of show some of these ideas from chapter 2. At least start here with this video. Now, much of the things I do in here, where did I get them? Well, I got to our page and I clicked the Sage quick reference link over here, and this has got a bunch of stuff. This is highlighted right here because I used it at one point. I highlighted and copied it, but so let's see what we have. So I just started with a 2x2 matrix and figured it was probably non-singular. We can try this with a singular matrix as well. So I said A is this 2x2 matrix. Down here, let's see, I never showed A, but then I made an identity matrix, and it's a 2x2 identity matrix. So I did that with identity underscore matrix and then 2 in the argument there. I called it IEYE. Actually, I think it might be Python that makes their identity matrix using a command that's EYE for I. But anyway, how did I know to do that? Well, I went here and I looked under matrix constructions, and I found this matrix identity. Let's see, I'll move a little more over this way. I found this thing, identity matrix of 5, and it says it's a 5x5 identity matrix and so forth. So, and notice here he makes a point of saying, they called it II because uppercase I is the square root of -1. So you don't want to use that as the matrix name or something like that. So so I made an identity matrix that was 2x2, and then I wanted to make that augmented matrix or the partition matrix. And how did I do that? Well, I said A dot augment with I, and what's that do? Well, how did I know what to do? Well, I went here, I found this thing combining matrices, and it says augment, and it says A dot augment B is A in the first columns, B matrix to the right. Okay, that's what I wanted to do. I wanted to do A and then the identity next to it. Now, if I needed to do them up and down, there's stack. There's this thing block sum, which is a diagonal thing, and even the tensor product. Okay, so there are various ways to combine matrices. I needed the augment one, so I did that, and then I showed it. And then I said, well, okay, let's just do the reduced row echelon form of C. We know how to do that. Of B, but assign it to C. And then I see what that looks like. And then when I look at that, I wanted the last 2 columns. And so how did I do that? Well, again, I went here, and there's pieces of matrices, and I looked, and I found this A matrix from columns, and I can list whatever columns I want. And again, remember the numbering of things starts at 0, and so I wanted the last 2 columns of a 4-column matrix, so they go 0, 1, 2, 3. So I wanted columns 2 and 3 to get my A inverse, and then I show that, and then I also show A inverse times A. So, if I hit evaluate, it goes through some things, and then we'll see some symbolic stuff down here. But so there's the augmented matrix. There's the reduced row echelon form. So I got the identity here. So this is non-singular. And there's the inverse. And so then I asked for those last 2 columns, columns 2 and column 3. And there's that. That's A inverse. And then I multiplied A inverse times A, and I got the identity. So that all seemed to work wonderfully. So then what I did was I just repeated this whole thing that I have here, but I changed A to a symbolic matrix ABCD. So I said var ABCD here in single quotes, and then set up a matrix ABCD like that. Now notice I didn't remake the identity matrix, didn't have to redo that, but everything else had to be redone. So I just copied and pasted it down below here, did exactly the same things. Here, notice I've got A inverse, and then A inverse times A, and then I've got this A inverse times A, and then in parentheses, and then I tell it to simplify full. And we'll see why, because when I ran that, so there's my augmented matrix. Here is at least one way one could write the inverse, as long as the inverse exists. Notice that if BC over A minus D, or in other words BC minus AD equals 0, the determinant equals 0, this doesn't exist. So we need AD minus BC to not be 0. But we got it there, and so then I took those last two columns. There's the inverse. It's not real pretty in this form, but there it is. And then I said take A inverse times A, and this is what I got. And the question is, well, is that 1 and that 1, and is that actually 0? And that's where now this isn't in the quick reference, I don't think, anywhere. I'm pretty sure it's not there. So I had to do some Google searching on simplifying and Sage Math, but that's where I was going to go up and look at that, but that's where I found the simplify full. And so sure enough, now I've used simplifying and so forth in Sage Math before without such beautiful results. Sometimes I get great results, sometimes I don't. And so here though, when I said simplify this whole thing, we see it is the identity matrix. So that was wonderful. And so, you know, just symbolically, you know, I have the solution for any 2x2 matrix that way. There are definitely better formulas than what came out here, but for the inverse of a 2x2, but it worked. Okay, now, so what if I have a singular matrix and do the same thing up here? So suppose I have 1, -1, and then 2, -2. We'll see what happens. Evaluate. Okay, I think everything worked. But so there's the augmented matrix. But notice I don't get the identity here on this left side. So this matrix shouldn't be the inverse. So I take that matrix out and I call it the inverse. I do the multiplication, and notice I get 1, -1. I do not get the identity. Okay, so whatever I end up with here in this augmented matrix reduction thing, when I multiply that times A, I get whatever's left over here. Well, it's not the identity, it's this, so that's not the inverse. And well, why not? Well, because that matrix doesn't have an inverse. Okay, so so there we go. And so that's kind of working with this idea of row reduction and inverses. It's pretty straightforward. Out of the, you know, we knew how to do the reduced row echelon form. Now again, this matrix up here and then the identity, I didn't have to do it with augment. I could have just done the full 2x4 matrix up here as matrix A with the identity tacked on, you know, to the end of it. But I thought, well, let's see that you don't have to do it that way. You can do it more modularly, you know, where the identity matrix you make separately, and see how we do that. And then we just augment the two together. But then once we do that, it's just our reduced row echelon form, and we can see the answer. But again, then we can let the computer pull the answer off of there to get our A inverse and go from there. But again, you need to check, because when this matrix up here A was singular instead of non-singular, it still did all this stuff, but we didn't have A inverse. So you do have to inspect it to make sure. Now let's see, that was a 4. And so let's also do, so here's show A inverse and show that. Let's do it, let's do a show A dot inverse. I think that should work. Seems like it should. If it doesn't, we'll get an error. I could go back here to the quick reference to check, but I'm guessing that will work. And so, there's our A inverse. Then we got the identity when we multiplied it together, and then we said, hey, SageMath, you compute the inverse, and look, same thing. So it's wonderful. We get that same result. Most likely because it's computing it essentially the same way, doing the reduced row echelon form and augmented matrix. Okie doke. So there we have some things with our row reduction and inverses. So we'll call that video done.